Hi, in this video we will discuss the properties of all the quadrilaterals that GMAT focuses on. So let's start the discussion with the first quadrilateral, that is square. A square is one of the most important and the most frequently used quadrilateral, and in a square the first few things that we need to know is that all the sides are equal, all the angles are equal, each angle is equal to 90 degrees. Now if we say that the side has length A, so the area of the square becomes side square. The perimeter of the square is equal to 4 times of side because all the 4 sides are equal. And then comes the most important part of the properties, and that is the properties of diagonals. Now there are 3 important points that we are going to discuss about the properties of diagonals in case of a square. The first is the diagonals are equal. The second is they bisect each other, and the third is they bisect each other at 90 degrees. So the very first and the important thing here is that this is the case, and this is a very special case in which the diagonals bisect each other at 90 degrees. That does not happen usually in every other quadrilateral. So that's the first case. Now the second case to discuss about the quadrilaterals is rectangle. Now rectangle has several properties. Let's quickly draw the figure first. So the rectangle looks like this kind of a figure which has some length, some width, the opposite sides are equal, each angle is equal to 90 degrees, and just another point to mention is that sum of the angles in any quadrilateral is always equal to 360 degrees. The property of area is L multiplied by B, where L and B are the length and width. The perimeter, because we have 2 sides equal to L and 2 sides equal to B, so the perimeter becomes twice of L plus B. And then comes the diagonals property. So the diagonals, in fact we should just learn this to identify the property rather than just memorizing the property. If you see the diagonals, now we can use the Pythagoras theorem as well to prove that both the diagonals are equal, because you see this diagonal will have length L square plus B square square root, and this diagonal will also have the same length L square plus B square and the square root of it. So the diagonals are equal. The second is they bisect each other. The meaning of the term bisect means that they divide each other in equal parts. So this part is equal to this part is equal to this part, both the diagonals are equal, so all 4 parts will be equal. And do they bisect at 90 degrees? Then from the figure you can understand that no, this angle is not 90 degrees. So we don't say that no, instead we say that they don't bisect not essentially at 90 degrees. So they don't bisect at 90 degrees essentially, however they may bisect at 90 degrees. Now the question is, what if they do bisect at 90? Now a rectangle in which the diagonals bisect each other at 90 degrees becomes a square. So we say that a square in a way is a subset of rectangle. Now let's discuss the third quadrilateral now. Yeah, and there is one more point to be added in rectangle. In rectangle, we have discussed in our exercise as one of the questions that all the 4 areas after you have drawn these 2 diagonals, all these 4 regions will have equal area. That means now we see the 4 triangles and all 4 triangles will have equal area, because you see if we consider half of the length of the diagonal as the base for these triangles, then the height is exactly same for all of them. For example, if you consider this as base, then this becomes the height. For this triangle as well, the base is equal and the height is common. So the area of all these 4 triangles are identical. The next case of the quadrilateral is parallelogram. Now parallelogram, as the name suggests, it has the parallel sides. So let's quickly draw the figure that is symbolic for the parallelogram. We have parallelogram that looks like this. So here the opposite sides are parallel and equal. Now the area of parallelogram is given by the property base multiplied by the height. Now here base is completely up to your choice. You can choose any side as base, and the distance between the base and its parallel other side is called the height. In fact, a parallelogram, if cut like this, forms exactly a rectangle. If you move this part triangle here after cutting this parallelogram from this line, it will become a perfect rectangle. So we are using the same rectangle formula as well, base into height. Now the most important part, the properties of diagonals. Now the diagonals, so now we should just question, are they equal? then you see if we mark this parallelogram as ABCD, then AC looks shorter than BD. So we say the diagonals are not essentially equal. Now, we say not essentially equal, that means they may be equal. And now the next question is, what if they are equal? Then a parallelogram becomes a rectangle perfectly, because when you keep moving these sides straighter, then there will be a scenario in which AC will have as much length as BD will have, and in that case we will get exactly a rectangle, and the angle between the two adjacent sides will be 90. Because it's a parallelogram, so the diagonally opposite angles in this case are equal, and the adjacent angles sum up to 180 degrees, so we can say that they are in a way supplementary angles. The properties of diagonals, let's come back to the same point. They are not essentially equal. Do they bisect? Then the answer is yes, they do bisect at 90 degrees. Then the answer is no, not essentially at 90 degrees. So they may bisect at 90 degrees. And the question is, what if they do bisect at 90 degrees? Then we come across a new figure that is called rhombus. Now, the definition of rhombus can be given in two ways. Rhombus is a parallelogram with equal sides, with all sides equal. So if we form a parallelogram which has the adjacent sides equal, then we get a parallelogram. That's one way to define rhombus. The second way to define the rhombus is that rhombus is a parallelogram with perpendicular diagonals. That means now there are only two scenarios of quadrilateral in which the diagonals are perpendicular bisector. So let me quickly draw a symbolic figure for the rhombus. So rhombus figure will look exactly like a parallelogram, except that since its all sides are equal, so it should represent that all sides here are equal. Now the property of diagonals. Now we can see that the two diagonals do not look exactly equal, so we say that the property of diagonals is that the diagonals are not essentially equal. Now the question is, what if they are equal? If the diagonals are equal in case of a quadrilateral, then we say that it's a square. So in a way, a square is a subset of rhombus and a square is a type of rhombus. So we will make this kind of a structure wherein we can define that what figure lies in what category in the next slide. So the diagonals are not essentially equal, but they do bisect each other, and they do bisect at 90 degrees. Now, there is also a formula for the area of rhombus, and that formula says that the area of rhombus can be calculated by half of d1 multiplied by d2, where d1 and d2 are the lengths of diagonals. Now this property comes from the property of area of triangles. For example, if we call one of the diagonals has length d1, then the half of the rhombus can be calculated, the area of it, half of d1 multiplied by d2 by 2, because we are looking at that d2 is this entire diagonal, so half of it will be d2 by 2, and the diagonals are perpendicular bisectors, so the half of the rhombus will be half of d1 into d2 by 2, and the full rhombus will be half of d1 into d2. So that's how we find out the area of rhombus. Now, having discussed this, there are two more quadrilaterals that we wish to discuss, and that we'll discuss in the next slide. So I'm just clearing this here, and the next slide, what are the next two cases that we have? So the next is trapezium. So you should know what is a trapezium. Trapezium is actually a quadrilateral, and the quadrilateral looks like, let me draw a symbolic figure. It has one pair of sides parallel, and we call them bases as well. So if we say that this side is A and this side is B, and the distance between the two parallel sides is h, then the only property that we need to know about the trapezium is that the area of trapezium is given by half of sum of parallel sides multiplied by the distance between them. The trapezium is basically a triangle cut off from the top. So if there is a triangle which is cut off from the top, then the remaining part here is a trapezium. So this is the only property that we need to know. And in a few questions I have seen the term like isosceles trapezium. Then we must understand that the two non-parallel sides in that case will be equal if the question ever talks about an isosceles trapezium. Now, the last part is a cyclic quadrilateral. Now, cyclic quadrilateral is a specific quadrilateral, and the special part about this is that the points, the vertices of the quadrilateral are cyclic. When we say cyclic, then it means that if you join them, you can form a cycle. Cycle means a circle. So the diagram of this figure can be represented in a way such as this. Suppose we have a circle here, and if we have a quadrilateral inside this circle, and even if none of its sides are parallel or equal, we call that this quadrilateral A, B, C, D is cyclic quadrilateral. The most important part of the cyclic quadrilateral is that in this case, the sum of the diagonally opposite angles, that means angle A plus angle C, is equal to 180 degrees, and similarly angle B plus angle D is equal to 180 degrees. And all four vertices, when joined together in a cyclic form, make a circle. So where do these properties emerge from? That we will discuss when we discuss the lesson of circles, because in that we will discuss where exactly does this property come from. However, now I would like to make this structure, and the hierarchy of the quadrilaterals can be given in this way. So I'm not discussing the trapezium and quadrilateral because trapezium essentially is not considered as a part of quadrilateral. It's basically a distorted triangle. So there is a debate whether trapezium falls among the category of quadrilaterals as such. So at the top we have the first generic quadrilateral that we can call a parallelogram. I think the figure itself will explain what figure we are talking about. And the parallelogram may have two of its subsets. Now one of its subsets becomes a rhombus because a specific parallelogram with all sides equal becomes the rhombus. So that's one particular case. And the second particular case of the parallelogram becomes a rectangle because a parallelogram with equal diagonals becomes a rectangle. And the specific cases of rectangle and the rhombus, they become a square. So we say that a square is in a way a subset of these two subcategories. Now let me quickly write them out. So here at the top we have parallelogram, this part is rhombus, this part is rectangle, and at the bottom we have square. So how we are defining it as that a specific type of a square, the square is a part of rhombus, a square is a type of rectangle as well. While rectangle is a type of parallelogram and rhombus is also a type of parallelogram, which means a square can be called a rectangle, a square can be called a rhombus, and a square can be called a parallelogram as well. And this is especially useful for the data sufficiency questions because they might give us some inputs to ensure that it's a square while the question is it a parallelogram? So let's not get confused that if the output is a square, then yes, it is a parallelogram because it's a type of parallelogram. Rectangle is also a type of parallelogram, rhombus is also a type of parallelogram. A specific case of parallelogram becomes a rectangle when adjacent sides are at 90. A specific case of parallelogram becomes rhombus when the adjacent sides are equal in parallelogram. A specific case of rhombus becomes a square when the rhombus has two equal diagonals or the adjacent sides making 90 degrees, it becomes a square. Similarly, a rectangle with perpendicular diagonal becomes a square, or a rectangle with two equal adjacent sides becomes a square. So that's how we set up the connection among different kinds of quadrilateral, and that summarizes all the quadrilaterals that we are going to come across while we are dealing with the GMAT question. Thank you so much for watching this video.